Hello, my name is Yusdiel Torres. I'm from Cuba, but I'm based in Berlin in the Leibniz Institute of Freshwater Ecology and Inland Fisheries. So let me first explain how I'm going to organize the presentation. First, I'm going to give you an overview of the research problem and also the modeling procedure. And then we are going to go through the code to see it in more details. Well, freshwater ecosystems represent just like less than 0.% of land surface. However, freshwater ecosystems host 6% of global biodiversity. So we can say that freshwater ecosystems are very important from the point of view of the biodiversity of the host. Freshwater ecosystems also are important for the services they provide to humanity. For example, in the case of recreation or water supply, but also thanks to the vegetation associated with basin and subbasins, freshwater ecosystems give us services like carbon sequestration, flood regulation, or soil retention. Unfortunately, despite they are so important, also they are among the most threatened ecosystems in the world. For example, these threats include habitat loss, or flow alteration and fragmentation because of the construction of some reservoir, as you can see in the image. Freshwater ecosystems are also threatened by contamination. This is a typical river in a Cuban city, sadly. And also are threatened by invasive species. This is the catfish. I prepared the version of this presentation in German or for a German audience. So this is why we have the German name here. So the main tool we have to protect biodiversity around the world are protected areas. But if you want to design an efficient system of protected areas, the first information we need is the species distribution. And in that case, we come with a problem known as the Wallacean shortfall in biodiversity conservation, which basically means that we lack of knowledge about the geographical distribution of most species, mainly of those that are threatened. The name of the Wallacean shortfall is because of Alfred Russel Wallace. Alfred Russel Wallace was Darwin's natural selection theory co-author. This is most known for this, but he is also one of the founding fathers of the biogeography. That was the name of that. It's because of the name of the Wallacean shortfall. So, how to try to solve this shortfall? Well, one tool we have for that are the species distribution models. And one of the inputs of these species distribution models are occurrences. So my idea in this project was to develop or perform species distribution model for a set of species from Cuba. And the first step was to compile a database with information extracted from literature, unpublished fieldwork records, museum collections, and online databases. And this is a summary of the groups we have in the database. Basically, insects, amphibians, crustaceans, and also flatworms. And in the pie chart, you can see that the proportion of the records distributed by each one of these groups. Well, in a species distribution model, basically you find the relationship between presence, pseudo-absences, and a group of predictors. And then with this relation in the environmental space, you use that relation to predict the presence or absence of a species in the geographical space. In the extreme side of the slide is then a general explanation of the workflow I follow to fit this model. There are a group of algorithms to model species distribution, but in this case, I use one called spatial linear stream networks regression. Basically, this is a generalized linear mixed model. The important idea here is that the model takes into account the spatial autocorrelation, but not just the spatial autocorrelation in following Euclidean distances, but also the spatial autocorrelation in the stream networks. So this is important for having species distribution predictions that represent the connectivity in the river stream, for example. Yes.
But in your combination, what do you mean, like the sort of logistic? That's what I mean. So when you're talking about linear dependence, right? Like I'm talking about like a model that could be used just like simple linear regression. That's what you're suggesting.
Yes, it's a linear regression. A logistic regression, okay. But that the error are modeled taking into account this spatial autocorrelation. Because usually when we model species distribution with all of these algorithms, we assume independence, statistical independence. But in practice, that assumption is violated because organisms are not distributed. I mean, they are frequently aggregated in the space, so you can have this violation of this assumption in statistics. So in order to train and test the model, the occurrences data were split in 80% for training and 10% for testing. And this was done 10 times in each species. And those, let's call it split, those splits that gives a good performance were then used to make the predictions. Here, the performance was evaluated with two metrics, AUC of the rock, it's area under the curve of the receiving operating characteristics, and also the true skill statistics. All both metrics are based on the confusion metrics. And then with with models that pass this performance test, then we build an ensemble of models of results for every species. And with the distribution of every species, we created a map of species richness.
So just so a picture I understand. So you're gonna run 10 different models of data. Is that right? For the ones that give a performance better than 0.7, you're gonna use all these models to create a sample and like use those to make predictions individually.
Yeah, that's it.
But is there any reason why you believe that a combination of these models is better than just using one of these models, since they all perform basically the same?
Yes, you can have variability, for example, due to the occurrences. So if you split your data set in that way, in case you have, for example, some outlier that could in somehow decrease the effect this outlier could have, because let's assume that the model that has this outlier is not selected because the performance is too low. So you can correct.
No, right, yeah, but like once you already have like, let's say out of the 10, you got 3 models that perform above 0.7. Why would you build an ensemble of these 3 models instead of just using one of them? You see what I mean? Since they all perform well, why would you combine them at that point?
Because we're not calibrated with the same points after all.
So they run different like samples for each.
Yes, because I'm splitting here, and
but the training is not the same data for all the 10 models.
yes.
And then test it with the same test set for all the 10 models.
Yes, for example, you have let's say 20 occurrences, and you randomly select, split in a group for training and another for testing. You do that once and repeat it again and again 10 times. 10 times. So in every time as you select this split randomly, you should have different combinations. Different combinations. And you do the so every time you do the training and testing.
Okay. So sort of like cross validation.
Yes, that is the idea. That is the idea. It's a kind of cross validation. It's a kind of cross validation.
Okay.
In SCDM, there are different techniques to do cross validation. One could be, for example, one leaf house cross validation, but this way is more recommended. So I follow this way. Well, all the analysis were, I mean, the spatial unit, I use it in all the analysis, was the subcatchments, and the subcatchments were extracted with grass geese, and this is a representation of the subcatchments. The scale to the left is like give you the area of the caption to have an idea. And this is the result of the sum of all modeled distribution of all species. Here I outline it, just those subcatchments which represent the top 10 species richness. So those are the most important from the point of view of the species richness. We could say that in those areas of Cuba, we have the so-called hot spot of species richness, and also should be important in terms of biodiversity conservation. So that is the idea of the work. Then I'm going to the part of the code. In the first part, I use a combination of GDAL tools, and also GRASS to download and crop and reproject the layers for predictors. As predictor, I use it bioclimatic variables, also from the CHELSA website of bioclimatic variables. I use it as I consider as important, at least in Cuba, because deforestation is covers like 8% of the island. So the presence of forest should be important for predicting biodiversity. So I use it here, a map of tree cover percent. With the digital elevation model and using GDAL-DEM, I calculated the slope. The slope is important for freshwater organisms because it's indirectly related with water velocity, and that with oxygen dissolved in water. And then in this part of the code, I crop and reproject all the layers I downloaded. Then in GRASS, first I set a GRASS session and extract flow, direction, accumulation, the strict network, and subbasins with functions in GRASS. This is, for example, the string network. These are the subbasins.
Can you remind me again what subbasin is? What's the definition of a subbasin?
It is the area that contribute to each of the stream ridge. Yes.
Yeah, so it's a small, I can't find now. Yeah. So it's all the area that is bringing the water into the single little stream. Yeah. Yeah.
And the color is just a random ID.
Yeah. Then in this part of the code, I aggregate all variable by subbasin. Basically, it's the mean. I use the mean of each predictor in a subbasin. Also, I did this with GRASS, running in a loop all the predictors. And these were the results. This is the percent of tree cover. This is the slope. This is flow accumulation. And these and the other and the rest of maps are bioclimatic variables. There are 19, usually are considered 19 bioclimatic variables, but in this case, I pre-select some of them that are not too much correlated, because this can be an issue when you model. And also variables that represented mean values for temperature, precipitation, but also that represented seasonal changes and daily changes. So that's why here you can see the annual mean temperature, but then you have the mean diurnal range of temperature. Temperature seasonality, annual precipitation, and also precipitation of the driest month, which is an extreme value and it is important. Well, the other part of the code mostly was run in R for here I did the predictions in the subcatchment, so I extracted one point at each subcatchment, and with that point I extracted the value of the predictors in that. And this code is for doing that. Then I generated pseudo absences following a procedure that is called two-step procedure. That first you do an environmental profiling. There are many methods to do that, but the most recommended is using, for example, one classification vector machine, and then from the less suitable areas for each species, from that area, I selected randomly the pseudo absences. So in that way, I got.
So you are already doing models for
Yes.
having this.
Yes, it is a model, but as I was mentioning at the beginning, the one that I use for the predictions has some possibilities, some characteristics that we want to use when we model species distribution of freshwater.
So
Which is this.
first you run one simple model, let's say,
Yes.
just to say the most probable and less probable places.
Yes.
From the less probable places, you pick randomly some
Pseudo absences. Yes.
to consider them as an absence.
Yes. Well, this R package, so run this model, it needs a special format and a special R objects. So you have to do some pre-processing first. And that pre-processing is doing with an R package that interact with grass. So in this case, I do this opening an R session, a grass session, and from within the R session, the grass session, I call R, and so here is the grass session. I import in the grass session some maps I'm going to need to create this object. Here, for example, I need to. I need that the column name is shorter than 10 characters, because the final output is going to be a shapefile. So that gives you an error if you have this. And in the following steps, then from within grass, I run the part of the R code. And all this is running in a loop, because I'm running for all the 131 species I modeled. And finally is the species distribution modeling, where I applied the model, I explained it before, but before running the model, I do some tuning of some of the parameters. For example, first, I do this with this R function I wrote. First, I do a stepwise regression to choose the best combination of predictors for do not have a too overfitted model. So I choose the best model with the value of the Akaike information criteria. So the model with the less, the lower value is the one I use. Then with the, I do here a second regression in the residuals of the first regression. The idea is that the part that is not explained by these predictors could be also explained by the spatial autocorrelation. So with this second regression, I try to find which of 200 possible combination of models that describe the spatial autocorrelation in the stream networks is the best for my data. This is a little bit computational intense, at least for R. So I run this in parallel. This is the script for running in parallel. This is a second function to evaluate the model, basically to calculate the AUC and true-skip statistics I talked at the beginning. And then here start a loop to run the model and run every one of these split for training and testing the model and finally produce the predictions. So that's the idea.
Esto se acabó.
No, I was a little bit sad because nobody was.
Wait. So any question for the public? So can you, so very good that you try to combine also grass and GDAL and R, also try to put your finger in Python. Can you point again when you did the second regression on the results, what you are trying to do? And let's see if the people also understand this concept.
Yes, because the spatial autocorrelation can be represented by different models that represent, let's say, spatial correlation that is influenced by Euclidean distances or distances along or across the stream network. Let's say the so-called as the distances measured as the fish swims or as the water flows. So there are a group of models that can be used to represent these spatial relations. Which one is the best for your data? You can, well, knowing something about the biology of your species, you can previously select some of these models. There are some models, for example, that represent basically as the fish swims. So in that case, if you are modeling a fish species, then you go only for that group of models. But in this case, we are modeling insects, we are modeling fishes, we are modeling amphibians. So here is relevant, could be relevant the distances across the stream networks. For example, for those insects that have larvae that lives in the water, which are bentonic. But these insects also has an aerial phase that can disperse as a crow flies. So the idea of this part is to try to select which one of these models fits the best to my data. And
Okay,
then
thanks. And one point to clarify. So you are building the first model, let's suppose with environmental predictors.
Yeah.
And then you are using the residuals versus spatial predictors like distance and so on.
Yeah.
So is it a lot long probably also? Is it clear the concept?
In
what
this
you're trying
case,
to
it's
do?
Yeah.
just one predictor. So in the second phase.
yes.
No, it can be
You
more.
just
So
want
different
a
kind of distance,
Yeah.
lot long, you know.
More than one.
Yeah.
Okay.
You get the value of the residuals and you use all the spatial context variables to keep training the residual. So in this way, you quantify, you are trying to model the spatial relationship that is not able to get from the first model. Okay.
Yes. And then with the information from the first regression and the second one, then you fit the spatial stream network model.
Okay.
Which is the
Okay, cool. Thank you very much.